So let's take a look at a few examples about how we can apply different integration techniques. And we'll start off with something kind of basic. We're going to write a Matlab program to do the Euler approach. And we'll start with this Rl circuit example. And we'll make some assumptions as far as circuit parameters, resistance of 40 ohms, inductance of 75 millihenries, voltage magnitude is 100 volts, so not very large. Frequency 60 hertz, 377 radians per second. I'll put an initial voltage angle on here as well. And as far as time steps, I mean, some stuff we need to be looking at would be, well, what are some of the different time constants and frequencies in the results? In this particular case, we got an RL circuit, so we're going to have a decaying DC offset. The time constant is 0.001875 seconds, so it'd be one thing to consider. So that's going to decay out according to that time constant. And then we have a 60 hertz waveform we're trying to capture in our results as well. 60 hertz, that would correspond to a period of 0.0167 seconds. And so, we want to take this into account. Maybe we would be looking at a combination of making sure that we had a simulation time that was at least a tenth of that 10 times less, 10 times less than that time constant. And then maybe we'd be wanting to make sure that we were capturing enough points, so we get kind of a smooth result in the sinusoidal portion of this. So as far as putting this into code, I'm giving you guys this code so you don't have to kind of take a whole bunch of notes from this. But basically the first part of this code is just kind of entering in the numbers. So this is set to be kind of like a little bit generic. I'm calculating an angle that's associated with the omega L over R. So that's going to be the shift in the current with respect to the voltage. In this case, I'm going to start off with a time step of 10 to the minus fourth in this. So it's kind of based on the time constant and the sinusoid I'm trying to capture. I'm going to go ahead and set this up where I can look at 3 cycles. And so if I get the period of the sinusoidal waveform, I'm going to calculate 3 cycles of that. And then I'm going to compare what I get with the Euler approach to what I would get if I just did this by hand. And so assuming we know already what this is, we don't have to go through this again. Basically, the Euler approach says that the update for the current at time t plus 1, the next time step is going to be the value at the previous time step plus the time step times the derivative of that current term, or this term minus RL times the current at the current step plus Vm over L times cosine omega t plus phi. That's going to be the derivative term. This portion here is going to give me the area for the update. And so I just put this into a loop. I'm just looping over a total time, and as far as the number of iterations I'm going to need, it's going to be the total time divided by the time step. When I'm done, I'm just going to go ahead and I'm going to do some plots. All right. So anyway, you can see it's not very complicated to program up. And you can see what I get as I get pretty decent results in this case. There's not a whole bunch of DC offset in this situation, maybe just a little bit of DC offset. But it actually converges pretty fast, and then it matches up pretty well with the calculated result. And so this was a pretty well-conditioned problem right here as far as applying electro-oil integration rule. Now let's make this a little bit more complicated. And what we're going to have this time is we're going to have an Rlc circuit. And what we're going to want to do is we're going to want to take a look at using an Euler approach in ODE 45. We're going to want to do some Matlab coding right here. And let's assume we start off with resistance of 40 ohms, inductance of 75 millihenries, capacitance of 10 farad. So this is just a series RLC circuit. We'll keep the source voltage the same at 100 volts. Still, we have the fundamental at 377 radians per second. We have a voltage angle at 6 degrees like before, but now that I have an RLC circuit, I'm going to get some transient ringing at a higher frequency in this case. And I'm going to plot this up to 3 cycles of the voltage forcing function. So again, if I were going to look at what to use for time steps, if I got a time constant of 0.0037, I'm not going to have at least something 10 times less than that for the time step. And then as far as natural frequency, the natural frequency turns out to be 1123 radians per second, which is going to be pretty close to 1 over the square root of L times C. And so if I want to plot a smooth part there, maybe I'd want to have a time step that's, maybe 32 times less than this in order to get a smooth output. But, those aren't really hard and fast rules. It's just some things to be thinking about. So for the code in this case, if I'm going to do the Euler approach, again, the Euler approach is pretty simple to implement. Basically all I need to do is have a basic update formula for both the voltage and current, so not too much to this. I'm going to have a time step of 5.5 times 10 to the minus 7th in this case. And then when I plot this out, for R equal to 40, what I'm going to get is this highly damped waveform because the resistance was so high. We get a little bit of an oscillation on this first cycle, but it damps out really fast because R is large. And then basically we see a 60 hertz waveform. Now, what happens if I drop R equal to 1? I'm going to have less damping in the circuit. Okay, it's going to be lightly damped. Now what I start to see is that high frequency component. I see the high frequency component superimposed on the 60 hertz. And so basically you see this high frequency part, it's kind of superimposed on the 60 hertz. And again, these results kind of make sense here as far as it looks kind of stable and everything else. So eventually it gets into kind of a steady state. Because the resistance is so low, it doesn't really damp out very fast. If you look at these peaks, it's kind of a relatively slow decay in this case. Now, what would happen if I played around with the time steps? And let's stick with the case for R equal 1 where we don't have much damping, and instead of having a time step of 5.5 times 10 to the minus 7th, I go ahead and try to get by with a time step that's going to be 100 times larger than that. So it's 5.5 times 10 to the minus 5th. What's going to happen? Well, it kind of starts to look like it tracks. It kind of looks like it kind of starts to track a little bit. But then what happens is it kind of blows up. All right. So all of a sudden, instead of these oscillations decreasing in magnitude, they actually start to increase in magnitude, and all of a sudden we get to the point where if we run this thing long enough, the magnitudes basically tend toward infinity. They don't really come back at all. All right. So what's happened in this case is, since I've chosen the smaller value of R, I'm getting, I guess, what we refer to as a stiffer set of equations that become more difficult to solve. And what's happening is we're not able to accurately calculate the area under the curve with this Euler approach, since the time step's larger. What happens is that error accumulates. So this inaccuracy in the integration algorithm in calculating the area under the curve, it builds up, and builds up, and what happens is the solution just diverges. And so if you guys were running, say, any simulation like PSCAD and that time step is too large, what'll basically happen is you'll have like a voltage or current just going to infinity, and you won't get anything that kind of looks like the solution you're supposed to see. All right. So anyway, this is what we have to watch out for in the Euler approach. We can get it to work if we keep the time step extremely small, but it's very prone to having error when you have these underdamped type of situations. If you want to do this in something like ODE 45, which is a Matlab function, all you really need to do is basically use this function, pass it a function that can be used to calculate the derivative. You would calculate the ending time that you want for this. You would give it the initial conditions. And then basically Matlab will actually use its internal algorithm to do this calculation for you. The way you would set up this derivative function is you would write your own little routine. Okay, this is your first order derivative routine. If you want to get the values in from the main program, I mean, you can declare these values as global. But basically what you're doing is you're just providing terms for the derivative of the voltage and the current, which in this case, I have set up as x prime. All right. So this is set up as kind of set up as a matrix right here. It's actually a vector, but basically you're going to have a first term and a second term, and then in terms of x, what you would do is you would write out the program for calculating the derivative. All right. So you have to kind of keep tabs on what x1 and x2 correspond to. When you do this now, what's kind of interesting about this is we get the right results. Okay, the results kind of make sense. It looks like we got before when we're applying the Euler approach, when we're keeping the time step small. But what's interesting about the ODE 45, if you look at the results, basically what it returns is it basically returns, if you can see it in here, yeah, you get a T out array and you get a Y out array. And what you're going to see in this case, sorry about that, is if you plot out time, and I plotted out time times 1,000. So basically what I'm plotting out here is I'm plotting out milliseconds. What you see in this case is the time step is not fixed. And so what it does is it starts out like with 0.1 microseconds. It does some initial iterations at these really small time steps. And then as time increases, and it gradually increases the time steps in order to speed up the time it takes to execute. So in the end here, you're using something more like 0.3, between 0.1 and 0.3 milliseconds for the time step. So anyway, what these Runge-Kutta algorithms can do, if you code them upright, is they could actually adjust the time step. And this will actually save you some time, because maybe it's just at the very beginning of this that you need to have the small time step in order to keep this solution from diverging. And then, once you get a little bit more in a steady state and you're kind of past the transit portion of it, then you can go ahead and you can kind of relax the time step and use larger time steps. So anyway, that's one thing you'll see in these codes, and even in Simulink, when you do Simulink simulations, if you use these variable time step algorithms, it'll actually adjust the time step as needed to give you a certain amount of accuracy. I'm also going to give you guys an example for the Runge-Kutta. And this is something that I put into a spreadsheet. Basically, I set this up where you have your input values that you can go ahead and plug in your own. Notice what you need to do is based on values of VC and IL at the previous time step. What you need to do is to get to the next time step, you need to calculate these various K factors. And since you have two variables in this case, you're going to have these 4 K factors per variable. You're going to end up with a total of 8. The reason I did this is I just wanted to kind of show people that you can actually do this stuff in spreadsheets as well. Now, this is not a variable time step algorithm the way I have it set up. It's a fixed time step, just because that's just easier to code up in something like Excel. But these numerical techniques, I mean, you can code them up. It doesn't have to be in Matlab. I mean, you can code this up in Excel. And so you're at work somewhere and you don't have access to the Matlab license, you could still do all this stuff in spreadsheets if you needed to. So anyway, if you look at these plots, you basically see these plots kind of match up what we got before using ODE 45 and also the Euler technique with an extremely small time step. All right, so the next thing I wanted to talk about is the use of Simulink, because we'll also be using Simulink this semester. Many of you probably used it before. It's based on Matlab. Simulink is kind of short for simulation and link, I guess. It's a graphical environment, so what you can do is you can draw things out in a block format, and then what Simulink has is it has a number of different routines that takes that drawing and converts those into formulas and solves those equations. A lot of what's in Simulink is kind of proprietary. You don't exactly see exactly what's happening under the hood as far as how it organizes the equations. You do see, you know, some of the integration techniques it uses, but you don't always know, you don't know exactly how it takes the figure and how it slices and dices it to get the solution. But the nice thing about using Simulink is that if you're good at writing MATLAB, like say like MATLAB M code, that you can actually integrate MATLAB M code into a Simulink simulation, or you can take the results of Simulink and you can dump them into MATLAB. And so it's kind of nice. It allows you to do a lot of custom programming. So we'll be using in this class the power systems modeling capability, and we'll talk about that in just a little bit some more. But anyway, here's the same example coded up in Simulink, and I'll have part C of the video where I actually walk through and show you guys how to build this particular circuit right here. Note one thing that's a little eye-catching right here is we have this little block here called Power GUI. This contains a number of routines that are needed to do the calculations, and also enables to set up like what type of simulation you want to use, technique you want to use, whether it's continuous variable step or maybe fixed time step discrete. But anyway, note what I have in the circuit is I have a couple measurement blocks in here if I want to get voltage and current. Kind of similar to what you have to do in PSCAD, but I've got to point out where I want the measurements at. And then this is a scope module, so I can actually see these plotted. This is also the circuit breaker element in this case. But anyway, once you get this set up in Simulink, then what you need to do if you go to modeling, model settings, is you could choose what type of integration approach you want to use. And so in this case, I've gone ahead and chosen ODE 45. This is variable step in this case. And one important thing to note when you're using Simulink and you're using these integration algorithms is you can set what you want the tolerance to be in terms of the accuracy of your solution. And so if you're setting this up, maybe by default it's going to have some sort of number like 10 to the minus third. So let's suppose we go ahead and run this with R equal to 40, R equal to 1. We get the same results for R equal 40, but one thing you'll kind of note in here, if you look at the R equal 1, which is kind of this underdamped case, is these waveforms are a little choppy looking. They should actually be nicer looking sinusoids. And so basically, since we didn't have that high of a tolerance, basically what Simulink did using ODE 45 would be it was looking for a time step it could use, you know, to get within that tolerance of 10 to the minus third, and it didn't see a need of using a really small time step for that. So if having a nicer looking plot's important to you, then what you would probably want to do is reduce that tolerance, make that tolerance number smaller. So anyway, if you go back in and you change that tolerance to 10 to the minus fifth, now you'll see we got the nice smooth curves in here. But what this is going to do, this is going to impact your simulation time. So it's going to take a little bit longer to run. So one thing you might want to look at is if you're not certain what the tolerance should be set to, kind of look at the formula or solution. If you see things like it's kind of fitting straight line segments together, if you're a plot, then you might want to consider dropping the tolerance a little bit. Another thing would be, what if you just set this up from scratch and you use default settings? And so there's something in here where you have like automatic solver selection. And so it's just going to do what it does internally and picks a solution technique, and you have the tolerance of 10 to the minus third. Well, if you run this, basically what you see, if this top is the voltage and this bottom, that's a forcing function, at this bottom's the current, you see it doesn't match at all what you expect to see as a solution for Article 1. So this is what we should have gotten, and this is what we got. And basically what you see is it didn't properly converge. The tolerance value wasn't set small enough. That's why, when we talk about this stuff, and you talk about setting time steps, you should always double check this. I mean, you should always change the tolerance and make sure that you're still getting the same solution. And obviously in this case, the program was giving us the wrong answer. So if you do change this tolerance, say you change the 10 to the minus fifth, I didn't check 10 to the minus fourth, but if you change the 10 to the minus fifth at least, you do get back to the right solution again. So again, it's kind of caveat emptor in the case that it's kind of up to you to make sure you're setting time steps and you're using the integration algorithms that are needed in order to get the solution to your set of equations. All right, so I'm going to go ahead and stop here, and what I'm going to do in the third segment is just kind of do a little bit of a walkthrough of how we would set this up and run this in Simulink.